Okay, this is a video for Chem 110 recitation. So if you are watching this video, you meet in my Monday recitations, and this week we do not have lecture because of Martin Luther King Day. So in lieu of lecture, I'm just going to make this quick video to go through the solutions to the problems, just in case you had any questions or concerns about how to possibly receive the answers that I've provided. And if you understand how to find an answer, there's no need to watch this. You can just skip around the video at your leisure to find the problems that you had difficulty with. So to start, the first problem, it asks you to draw the strongest intermolecular forces in a solution of 1,4-butane-diol and calcium chloride. So calcium chloride, as we know, is a salt solution, and you have positively charged calcium that forms an ionic bond with chlorine. So what happens? We have butane-diol, and this solution has, or this molecule has two polar bonds, one between this OH and another one between this 2H. So what's going to happen is you will have calcium and chlorine ions in solution. And this butane-diol is going to associate itself and form solvent shells around these two ions, so that the partial negative on the oxygen faces the calcium and the partial positive on the hydrogen faces the chlorine. So we would have a molecule like this, and we'll just draw the hydrogens off to the side here. So as we know, the OH bond, the hydrogen has a partial positive and the oxygen is a partial negative. So these partial negatives are attracted to the positive calcium, and we'd have something similar form possibly up here with the same thing. And so this is an ion dipole bond forming between these oxygens and the calcium. The same thing would happen with chlorine, except you'd have the hydrogens oriented towards it. Because these partial positives would orient themselves towards chlorine. So that would be an ion dipole association forming solvent shells. And so now it asks, will the solution have a higher or lower boiling point than a solution of pure 1,4-butane-diol? So essentially what this is asking is it wants to know, would a solution of pure butane-diol have higher intermolecular forces than this mixture of this compound with the ion calcium chloride? So basically, if we just had a solution of this, you would have hydrogen bonds form between OH groups. So one OH group on one molecule would form a hydrogen bond with another OH group on another molecule, and we would have carbons behind both of these. So in a pure solution, the strongest bond we would form is a hydrogen bond. All right, and as we know, the second strongest intermolecular force you can form is a hydrogen bond. But in this mixed solution of the ion with the 1,4-butane-diol, we're forming ion dipole bonds. And ion dipole bonds are the strongest bonds you can possibly form as an intermolecular force. And therefore, this mixed solution would have stronger IMFs. And because of that, it would have the highest boiling point. Okay, so that's the first question. Second one, it's asking you to draw the 5 possible hydrogen bonds between water molecules and this molecule here. So just so I don't have to redraw it, I drew it in advance. And so as we know, hydrogen bonds form between a donor hydrogen and an acceptor molecule. So this acceptor molecule or acceptor atom has to be a nitrogen, oxygen, or a fluorine. And this donor hydrogen, it must be covalently bonded to an oxygen, nitrogen, or fluorine. All right, so water molecules have the following structure where you have two hydrogens bound to one oxygen, and both of these hydrogens are partially positive, as we know. And so both of these hydrogens can form hydrogen bonds with acceptor atoms. So on this molecule, we have two oxygens. So this oxygen here is not covalently bound to any hydrogens, so it will not be a donor atom. However, it can accept hydrogen bonds from a water molecule. So a good way to go about this is to think that each lone pair on an acceptor atom can receive one hydrogen bond. So we have one lone pair here and another one here. So we could have a water molecule here, form one hydrogen bond with that lone pair, and another hydrogen on this water molecule here, form another hydrogen bond. So we have 2 hydrogen bonds so far, and it says there's 5 possible. So the next one, we have this hydroxyl group on this benzene ring here, and this oxygen is the same as this one up here. It has 2 lone pair groups, and each of them can be a donor for another water molecule. So both of these can form hydrogen bonds. And this oxygen atom is also covalently bound to a hydrogen. So this hydrogen can be a donor for another water molecule. So in this case, this water molecule would hydrogen bind from the oxygen to the hydrogen. All right, so that's the 5 water molecules. So if you see a question like this on a test, basically just remember that oxygen, nitrogen, and fluorines, they don't have to be bound to a hydrogen in order to accept a hydrogen bond. They just have to be bound if they're going to be a donor group. Okay? All right. So next question. This question is about DNA. So with DNA molecules, we have 4 bases. We have adenine, thymine, guanine, and cytosine. Purine and pyrimidine groups, if you're not a biology major, don't even worry about the details. But basically the way it works out is that thymine and adenine bind to one another, and they form 2 hydrogen bonds. And guanine and cytosine like to bind to one another, and they form 3. So the question asked is, let's say we had a DNA molecule that had a high amount of guanine-cytosine bonds compared to the adenine-thymine. How would this melting point of this DNA molecule compare to another DNA molecule that had more adenine-thymine bonds? So as we said, adenine-thymine will form 2 hydrogen bonds, and guanine and cytosine will form 3. So each additional hydrogen bond actually makes the molecule more stable. So this guanine-cytosine interaction up here is more stable than this. So it has higher intermolecular forces. These 2 molecules are attracted to each other more than these 2 molecules, simply because this can form 3 hydrogen bonds and this can only form 2. So if we had a DNA molecule that had a high amount of guanine and cytosine, so GC, its melting point, it should be higher than a DNA molecule with a lot of adenine thymine. And that's simply because this GC bonds will form 3 hydrogen bonds compared to 2. So if you have more GC, it's going to take more heat to break those hydrogen bonds. So because of that, the melting point will be higher. All right, question 5. Rank the following molecules in order of increasing vapor pressure and increasing viscosity. So first of all, before we do anything, let's rank these molecules according to their intermolecular forces. So as I said in recitation last week, if you see just a single molecule and it's asking you about its IMFs, what it wants you to do is it wants you to assume more than one. So this is propane. We would assume we have 2 propane molecules. So the question would be, how will these 2 interact? Well, propane is a nonpolar molecule, so this would simply be dispersion. Okay, and D over here, this is butane, and butane also only interacts with dispersion. So both of them have the same intermolecular force. However, butane is larger than propane, and so because of that, it will have higher intermolecular forces than propane will. Okay, now we have C and B. So both C and B have a carbon bond bound to an oxygen, and both of these will form polar bonds. So both of these molecules will display dipole-dipole forces, okay? So they have the same intermolecular forces. They have dipole-dipole and dispersion. So how do we rank them on increasing intermolecular forces? Well, they have the exact same bond between both of them. It's a carbon-oxygen. So they should relatively form the exact same strength of a dipole moment. So we would expect their dipole-dipole interaction to be similar. So how else can we compare them? Well, we can compare their dispersion forces because, as you remember, all molecules will have dispersion also. So this molecule here, this is 2-butanone. This has an extra carbon than propanone, 2-propanone. And so because of that, it has a higher molecular weight. It has more electrons. And so this molecule will have higher dispersion forces. So if we're just ranking them on the higher intermolecular forces, this is the highest, followed by this, followed by this, and followed by this. Okay? Now we need to assign that based on vapor pressure and viscosity. So the trend that occurs is the more intermolecular forces you have, the more viscous something is. So as intermolecular forces increase, the viscosity will increase also. This is because viscosity means that it's a thick liquid, and that's just caused by the molecules sticking together more, which makes it more viscous. So for the viscosity, it would be the exact same order. B would be greater than C, which would be greater than D, which would be greater than A. All right, so viscosity has the exact same trend as melting point and boiling points. It increases with increasing intermolecular forces. Now, vapor pressure is the exact opposite. As intermolecular forces increase, vapor pressure will decrease. This tends to be something that causes a little confusion. You may think, why does it do that? Why is it opposite? So let's just imagine that we had a beaker of water here and another beaker of hexane. Okay, so structure of water and the structure of hexane. Okay, so as we know, water will form hydrogen bonds. Hexane will only have dispersion interaction. So we can confidently say that water will have higher intermolecular forces than hexane will. Now, if we put a cap on both of these beakers and we created a vacuum, so we removed all the air from both of these beakers, what would happen is that some of these molecules in the water would evaporate. All right, as Dr. Kaut said, if you just leave a glass of water, it doesn't have to be boiling necessarily to have evaporation. And these water molecules would exist above the liquid because you have a lid on it. It can't leave. And as we know, according to the ideal gas law, as you increase the moles or the amount of molecules in a gas, this will increase the pressure. Okay? So as the moles increase, the pressure increases. So the more molecules we have that evaporate, the higher the vapor pressure will be. Now, because water has higher intermolecular forces, remember that the boiling point increases because of that. So these water molecules in a liquid like to stick together. So if one of these particles tries to escape and become a gas, it's going to be held back more strongly than hexane by its strong attraction for other water molecules in the liquid phase. So because of that, these hexane molecules, they can escape more easily from the liquid and become a gas. And so you will have more gas molecules that exist in the hexane. And because of that, this vapor pressure will be higher in the hexane beaker than it is in the water. Okay? So I know that is slightly complex, so if you have any further questions about that, I'd be happy to explain that to you in my office hours. That should be on Tuesday. I'll send you guys an email. So Because of that, the trend is opposite. So with the vapor pressure, the one with the greatest vapor pressure will be A, propane, followed by D, followed by C, followed by B. So B, the one with the strongest intermolecular forces, has the lowest vapor pressure. All right? All right, next question, 6. So Mark Watney is stranded on Mars. Commander Lewis left him to die. So he needs to create water for his potato farm. So he pumps hydrazine, N2H4, from the MAV pad into the HAB in order to use it to create water. So I just want you guys to draw the structure of hydrazine and tell me which intermolecular forces are present. All right, so first the structure of hydrazine. These nitrogens will not be terminal because hydrogen usually is always terminal. So we'll have 2 nitrogens in the middle. Okay, each of these will have 2 hydrogens bound to them. And there will be a bond in between these 2 nitrogens. And both of them will have one lone pair. All right, so the orientation of this molecule in 3D space is you'll actually have this nitrogen with 2 hydrogens kind of pointing downward. Okay, and this nitrogen should have the hydrogens pointing upward. All right, so this nitrogen is going to create a dipole moment between both of these hydrogens upward. Okay, so this should be partially negative, this should be partially negative, and all the hydrogens will be partially positive. So it's not as simple as just saying this molecule is linear, therefore it's not polar. You have to look at this. Both sides, both this nitrogen and this nitrogen, will be withdrawing electron density. So what's going to happen is that the terminal hydrogens are both going to be slightly positive, and this middle with the nitrogens is going to be partially negative. Okay, so this is actually indeed a very polar molecule. Okay, so what you're going to have is, obviously it has dispersion, everything has dispersion, and as I said before, it's a polar molecule, so you will have dipole-dipole. And because this nitrogen is bound to hydrogens, you're also going to form hydrogen bonds. Okay. Now, if we wanted this to have ion dipole forces, we would need to add a salt. So basically, if you read a problem and you don't notice a salt, you're not going to have ion dipole. But if we added a bunch of sodium chloride, we would form ion dipole interactions. Okay, but currently we don't have those. Okay. Now the next question. So this is asking you to determine all the kinds of intermolecular forces present in each compound and rank them from highest to lowest, boiling point, and vapor pressure. So as I explained, vapor pressure has the opposite trend with increasing intermolecular forces than everything else you learned has. So boiling point will increase with increasing intermolecular forces. So before we do that, let's determine the intermolecular forces in each molecule. So we know that water, and I'm actually going to move this down just so I don't stain the table. We know that water has a bent shape, and because of that, it forms a dipole moment. So it's going to be dipole-dipole, and of course, it's going to be hydrogen bonding. And it'll also form dispersion because all molecules form dispersion forces. All right? So that's water so far. Now, the next one, this is propane. This is just 3 carbons bound to one another. I keep screwing that up, sorry. And each one is bound to hydrogens. So there's not going to be any polar bonds. So because of that, the only IMF you'll have in this molecule is dispersion forces. Okay, now the final one, this is CH3, CH2, Cl. So we have 2 carbons bound to a chlorine. All right, so this will form dispersion forces and dipole-dipole because this chlorine is bound to a carbon, and the difference in electronegativity between chlorine and carbon is great enough that this will form a dipole moment. And this chlorine will be negative, partially negative, and the carbon will be partially positive. All right, but this chlorine is not bound to any hydrogen atoms, okay? I need to make that clear because when you look at the chemical formula, you see a CH2 following a Cl. So you would be tempted to say the Cl is bound to a hydrogen. Now that I think about it, in this case, it wouldn't matter anyway because Cl, as we know, will not form a hydrogen bond. But let's imagine this was a fluorine. You might be tempted to say the molecule could form hydrogen bonds just based on the way the structure is wrote out. But that is not the case. All right, the next one, CH3, CH2, OH. Now, this one has 2 carbons bound to an oxygen, which is bound to a hydrogen. All right, so this oxygen has a dipole moment with this hydrogen, and as we know, an OH will form hydrogen bonds. So it has dispersion because everything has dispersion. It has dipole-dipole because you have a dipole moment between this oxygen and hydrogen, and you have hydrogen bonding because you have a hydrogen bound to an oxygen. Hydrogen bonds, oxygen, nitrogen, fluorine, okay? Last one, 2 carbons. Okay, so both these carbons are bound to hydrogens. And there is no dipole moment. All you have is dispersion forces. All right. All right, so I realized that the camera wasn't panned down here, so I stopped, restarted. If this page looks different, it's because I previously worked through the entire video and finished it, and right before I saved, my phone died, so I lost a lot of time. So anyway, I'm redoing it now. So as I said before, this one here, this is ethane, and it doesn't have any polar bonds, so it simply has dispersion forces. Let me check these really quickly. Sorry about this. Okay, so now that we have them all drawn, now that we have all the intermolecular forces figured out, now we need to rank them according to boiling point and vapor pressure. So as we look at these, we have water and we have ethanol. So both water and ethanol have hydrogen bonding. As we know, hydrogen bonding is the second highest intermolecular force. And in this case, out of these 5 molecules, that would be the highest. So how do we decide between water and ethanol which one has the highest intermolecular forces? Well, if we look at water, we notice that this oxygen is bound to 2 hydrogen atoms. And with ethanol, the oxygen is only bound to 1 hydrogen. So because oxygen is bound to 2 hydrogens, this molecule could actually form 4 hydrogen bonds. Both of these lone pairs on the oxygen, this one here, can form a hydrogen bond with another water. This lone pair can do the same thing with another water. All right, and then both of these hydrogens can form hydrogen bonds with oxygens of waters, okay? So this molecule of water can form 4 hydrogen bonds, okay? Now ethanol has an OH, okay? So this oxygen is only bound to 1 hydrogen. And so this oxygen has 2 lone pairs, and each of these lone pairs can form hydrogen bonds with other H's from other ethanols, okay? But it only has 1 hydrogen, so it can only form 1 additional bond to an oxygen, okay? So this ethanol can only form 3 hydrogen bonds with itself. So because water can form 4, we're actually ranking water as higher. So water would have the highest intermolecular forces, okay? And ethanol would be the second highest, okay? Because these are the only 2 with hydrogen bonding. Now, the next one, CH3CH2Cl, has a dipole moment. So this would be our third highest intermolecular force because the other 2 are just dispersion forces. All right, so now we have propane and ethane. Okay, And propane has a higher molar mass, therefore it has more electrons and a higher dispersion force. So this would be our fourth highest, and ethane would be our lowest. Now, to rank them according to boiling point, as we know, as intermolecular forces increase, boiling point also increases. So this will be ranked the exact same way as our IMFs. Water will have the highest boiling point, followed by ethanol, followed by CH3CH2Cl2, okay, followed by propane, and lastly, followed by ethane. Now, for vapor pressure, as we previously discussed, the trend is opposite. So the molecule with the highest vapor pressure would actually be ethane. Okay, next highest would be propane. All right, followed by CH3Cl2Cl, followed by ethanol, followed by water. So water, the molecule with the highest IMF, has the lowest vapor pressure. All right, so next, you're asked to arrange these compounds in order of decreasing viscosity. Okay, so, and also explain your reason according to IMFs. So if we look at these compounds, this molecule of ethanol can form hydrogen bonds. And as we discussed previously, because it has an OH, the oxygen can form 2 bonds and the hydrogen can form 1. So this can form 3 bonds total. Now this is just butane, just 4 carbons in a chain. So all of these are nonpolar bonds, so this is just a dispersion force. All right, the next one, this is called a diol, which means it has 2 hydroxyl groups. And so it's just a hydroxyl, so an OH, bound to 2 carbons, bound to another OH. So this also has hydrogen bonds, okay, because of these OH groups. And each OH group can form 3. So because it has 2 OH groups, this could form up to 6 hydrogen bonds. And the last thing is this ether. It has an oxygen in between 2 carbons. So you have a CH3 bound to an oxygen, bound to a CH2, bound to a CH3. And because of the shape of this molecule, the bent shape that the oxygen lone pairs impose on the carbons, you have a dipole moment in each of these bonds and a net dipole going up. So this molecule would have dipole IMFs. Okay, so if we arrange these 4 in order of decreasing viscosity, so which one would have the highest viscosity? Well, the one with the highest viscosity is going to be C, because C forms up to 6 hydrogen bonds. Okay, next highest will be ethanol, A, because ethanol can form up to 3 hydrogen bonds. All right. Next, we have this ether molecule, because it's a dipole-dipole. And lastly, we have butane, because all it has is dispersion. All right, so 1, 2, 3, 4. Okay, this is the highest, this is the lowest. All right, the next one, it says arrange these compounds in order of increasing surface tension. I don't like that. Let's say decreasing. Let's just order them the same way as we did before. So in this case, 1 would have the highest surface tension. So I don't believe I've talked about surface tension yet. Surface tension is basically when a liquid resists an object placed on top of it. So if we have a lake, if you've ever been to like a pond or a lake, you always see these little water bugs that can basically walk on water. And the reason this is possible is because this water has such a high surface tension that it resists this animal falling through. And the reason IMFs are important is because the strong bonding of water to itself causes these molecules to rather stick together than cause this animal to fall in and cause them to spread out. So as intermolecular forces increase, surface tension also increases. Okay? So yeah, I mean, you can float paper clips on water. That's because of water's high surface tension. Okay, so let's do the same thing where we arrange them by the intermolecular forces first. So this molecule here has a fluorine. So as I said before, it's important to realize that you see a CH2 here, and after the CH2, there's an F. So when you're just looking at the chemical formula, it's tempting to think that this fluorine may be bound to a hydrogen, but a CH2 always means you have two hydrogens bound to carbons. So this fluorine is bound to the carbon, not to the hydrogens, okay? So a CF bond is has a high difference in polarity. I'm sorry, a high difference in electronegativity. So this will be a polar bond. So you will have a dipole interaction. And by the way, I'm only writing the strongest intermolecular force. Obviously, all four of these would have dispersion. I'm just doing that to save time. I'm only writing the strongest IMF for each one. Now, the next one, this is butanol. So you have 4 carbons attached to a hydroxyl. All right. So this hydroxyl group will be able to form hydrogen bonds. So hydrogen bonds will be the highest IMF. Okay. The next one, we have 5 carbons in a row. So we have pentane. Okay. And then this, we have a carbon with 4 CH3 groups grouped around it. So both of these will be dispersion. So the question is, which one will have the highest dispersion force? So if we look at the molecules, they seem to have similar molar masses. They each have 5 carbons. And let's see, 3, 6, 8, 10, 12. Yeah, 12 hydrogens. So they both have the same molecular weights. So if they have the same molecular weights, we have to look at their structure to figure out which one has highest dispersion. So this is a chain of 5 carbons, okay, in a row. And this here is a carbon with 4 CH3 groups spread out across it. All right. So because this molecule will be more spread out, the carbons are in a chain, it will have higher dispersion forces because it has a higher surface area of interaction. Okay, so if we were to rank these now, this molecule here, butanol, will have the highest surface tension, okay, because it has hydrogen bonding, the highest IMF. Following that, this molecule with the fluorine-carbon bond will be up next because it has dipole-dipole. Then our pentane will be the 3rd highest, and then the CH3-4 will have the lowest surface tension, okay, because it has the lowest intermolecular forces. All right, so now we have questions on cohesion and adhesion. So a quick review on cohesion and adhesion forces. So cohesion, okay. Cohesion is, let's just use a liquid. It's when a liquid sticks together. So if we have water, the water tends to stick together. If you ever get drops of water in your hand, you'll notice that they tend to like beat up and form like circles, balls on your hand instead of just spreading across it. That's because the cohesion of the water attracts it to itself rather than to your hand. Now, adhesion is the attraction of a liquid to a surface, okay? So if we put water on this paper, what would happen is the water would spread out on the paper. It would sink in, and that would be because the water's adhesion for the paper is strong enough that it will separate from itself and spread out through the paper. So in the case of that, so if we put a drop of water, it would spread out, okay? That's because the adhesion forces of water for paper are stronger than water's cohesion forces for itself, okay? So the first question, it says, if water wets or spreads across some surface, does it have stronger cohesive or adhesive forces? So as I just said, if it spreads across the surface, it would have stronger adhesive forces. All right, next question. It says, if mercury beads up on some surface, are there stronger cohesive or adhesive? So by bead up, that just means that the mercury will just form kind of a ball on the surface. In that case, the mercury is more attracted to itself than it is to the surface, so it would have stronger cohesive forces. The next one, it says, if water forms a concave meniscus in a clean glass tube, are there stronger cohesive or adhesive forces? And D says, if mercury forms a convex meniscus. Okay, so what's the difference between concave and convex meniscuses? So if we had two vials, I'm actually going to zoom out, make this easier. So if we have two vials, here's one vial, here's another. Okay, and let's say that this vial has water in it and this vial has mercury. So a concave meniscus would be something like this. Okay, so the water kind of bunches out towards the sides and it's lower in the middle than it is on the sides. A convex meniscus is the opposite. The mercury in this case would bulge in the middle and spread in rather than out. So in this case, with the concave meniscus, the water is attracted to the edge, to the surface of the vial, and spreads apart because of that. So in that case, the adhesive forces would be stronger. So the adhesive. Okay, and for the mercury, when it bulges up, it's attracted more to itself than it is to the sides, the surface of the glass vial. So in that case, the cohesive forces would be stronger than the adhesive. Okay. Now, the final question given is based on the Clausius-Clapeyron equation. Sorry if I said that wrong. And so this question is going to require you to use a graphing calculator. You'll use graphing calculators quite extensively in this course, especially towards the end. And what you're going to have to do is you're going to have to run a linear regression test. Now, if you've taken a stats course, you most likely know what that means. If not, don't worry. It's not a big deal. What a linear regression is going to do for us in this moment is it's going to give us the line of best fit on a linear line. So, first of all, the Clausius-Clapeyron whatever equation is expressed as the natural log of the pressure vape. Okay, so the vapor pressure, that's equal to the enthalpy of vaporization divided by R, and that's the negative enthalpy of vaporization, by the way. Okay, times 1 over T plus the natural log of beta. Okay? Now, so this is one of the scariest equations you'll see in Chem 110. There's some others that are pretty bad, but it's actually not as horrible as it seems. So let's just start. Let's say this natural log P of vaporization is our Y. Let's say this delta H of vape over R is our M. Let's say this 1 over T is our X. And this natural log of B of beta is our B. So you'll recognize this as the linear line formula that we were taught in junior high and high school, where Y, the intersection on this line, X, the intersection on this line, and M is the slope of the line, and B is the y-intercept. Okay, so if we graph 1 over the temperature in Kelvin versus the natural log of the vapor pressure, we can obtain a linear line. And if we solve for the slope, we can find the enthalpy of the vaporization. Okay, so to start out, if you have any questions over the process of this, I believe there's a guide, page 195 or 295 in your recitation. Can't remember exactly, but to start, so here's our table, and it gives us our temperatures in Kelvin and our vapor pressures in torrents. So our x-axis plot is going to be 1 over T, and our y-axis plot will be the natural log of the vapor pressure. Okay, and like I said, that's because this is equal to our y in the linear equation, and this is equal to the x. Okay? So we'll use our calculators. And to start, you'll hit Stat. Okay, and that's going to open up this page. Click Edit, so hit Enter. Okay, and if you have lists already put in, you need to delete them. So go to the top, hit Clear, Enter, and that should delete it. Do the same thing with this one, Clear, Enter, and now we're ready to put in the data. So to start, I'm going to put in the data for the temperature in Kelvin. Okay. Oops. Sorry about that. Honestly, it's lucky that hasn't happened yet. All right. So I'm going to put in the data for x, 1 over t. So I'm going to take these numbers and I'm going to take 1 divided by them. So 1 divided by 255. Okay. 1 divided by 265. 1 divided by 275. 1 divided by 285. 1 divided by 295. And 1 divided by 300. Okay. Now we're going to do the same thing for the vapor pressure, except we're going to take the natural log of these numbers. So I'm going to take the natural log of 11.3, natural log of 21, natural log of 36.8, natural log of 61.5, and the natural log of 99, and one more, 123.8. Okay, so now you should have your L1 and your L2 graphed. So after you do that, you click Stat once again, and you go over to Test, and you can go to the very bottom or just click Up, which will take you to the bottom, and go to the linear regression t-test. Okay, so you click that. Now it has your X list and your Y list. So it says L1 for X and L2 for Y. So you basically want that to match these L1 and L2 up here. If that doesn't match, you need to change that. And the way you do that is you simply click Second Stat, which opens up the list, and you can change them with these variables here. All right, so if that's improperly, don't really worry about the frequency or the zeros or anything. Just hit Calculate. Okay, and that will give us all this. So it gives us the A and the B. So if we look at this, the B here, that's our slope, and the A is the y-intercept. Okay, so B is the slope. So ask for the slope. B equals negative 4,063. Give me a sec. 0.867. Okay. So negative 4,063.867. And the y-intercept is equal to 18.373. That's because of the A being equal to 18.373. All right, so now that we have that, it asks us to find the heat of vaporization. So as I said before, this heat of vaporization, the negative heat of vaporization divided by R, which is a constant, is equal to M. M is equal to your slope, right? So another way of saying that is that the slope is equal to negative delta H vaporization divided by R. Now, said R is a constant, and that constant is equal to 8.314. That's joules per mole degree Kelvin. If you don't know what this joules per mole degree Kelvin is, don't worry. It's just something you kind of have to memorize. So if we use algebra, if we multiplied this R over, so if we did the slope times the R, that would be equal to the negative delta H of vaporization. Okay? So we said the slope was equal to negative 4,063.867. Negative 4,063.867. And the R is equal to 8.314. All right? So we get negative 33,786.9. So we'll just say 87. Now notice that that's equal to the negative delta H. And so since this is a number, negatives cancel. So we can just multiply this by negative 1 to turn it into a positive number. So the heat of vaporization is equal to 33,787. All right. Now, this is very important. If you solve for this heat of vaporization, because the constant you used was in joules per mole degree Kelvin, this answer is in joules. Okay? And we will always ask you to find this answer in kilojoules. Okay? So you just have to convert this to kilojoules. It's relatively simple. Just take 33,787 joules times 1 kilojoule for every 1,000 joules. Okay, so you should just get, so just take this number divided by 1,000, and you get 33.787 kilojoules. All right, so that's the final answer. Okay, so that's everything I have for you. I hope this was helpful. If you have any further questions, feel free to send me an email or stop into my office hours, which I will send you an email for this upcoming week as soon as I figure that out. So, yep.